In this video, we're going to do example 3.4.4, where we are asked to use the definition of differentiability to show that the function f of xy, which is x plus 2y squared, is differentiable at the point 1, 1. So let's remember the definition of differentiability has this error function, e of xy, which is f of xy, minus essentially the expression that would be the tangent plane. So f of AB plus f sub x of AB times x minus a plus f sub y of AB times y minus b. And what we have to show is that the limit as xy goes to AB of this function e of xy divided by the square root of what is essentially the distance, x minus a squared plus y minus b squared, that this limit is 0. So that's what we need to do. So the first thing we're going to do is create our error function e of xy. So let's take the pieces. First of all, our AB is the point 1 minus 1. So f of AB is 1 plus 2 times minus 1 squared, or 3. We need f sub x. So f sub x at any point xy is, we're taking the derivative here of x plus 2y squared with respect to x. The 2y squared disappears and the derivative of x is just 1. So f of our point 1 minus 1, f sub x, is just 1. F sub y at any point xy is, well, the x disappears. We take the derivative with respect to y, and we're going to get 4y. So f sub y at the point 1 minus 1 is 4 times minus 1, or minus 4. We can build our error function now. So e of xy is f of xy, which is x plus 2y squared, minus all of this. So minus f of AB, that's 3, plus f sub x, which is 1, times x minus a, x minus 1, plus f sub y, so minus 4 times y minus minus 1, y plus 1. Now, if we simplify this a little bit, we are going to get x plus 2y squared minus 3 minus x plus 1 plus 4y plus 4. Collecting our like terms, well, we are lucky that some stuff cancels, so our minus x and our plus x will cancel. And we will end up with 2y squared plus 4y. And then what's left is minus 3 plus 1 plus 4. That's 5. Minus 3 is 2. So plus 2. Now we can factor out a 2, which gives us y squared plus 2y plus 1, which we might recognize as a perfect square. So we can write our function e of xy as 2y plus 1 all squared. Now we need to examine this limit. So this limit is going to be, well, the term of that limit, e of x y over the square root of x minus a squared plus y minus b squared is going to be 2y plus 1 squared over the square root of x minus 1 squared plus y plus 1 squared. Now, to evaluate the limit of this as x goes to 0, we are going to appeal to the Squeeze theorem. I know how you have missed that from your first calculus courses. We can first of all set up an inequality. Everything here is non-negative. And so 0 is going to be less than 2y plus 1 squared over the square root of x minus 1 squared plus y plus 1 squared. And that is going to be less than or equal to, I'm going to create a new function here. We have a y plus 1 squared in both the numerator and the denominator. I'm going to add in a missing x minus 1 squared up top. So 2y plus 1 squared plus, and I'm going to add in 2 times x minus 1 squared. Now, how come I can do that? Well, I can add anything that is positive because I'm creating an inequality. So as long as what I create here is bigger than what I have over here, I'm just fine. The question is more, why would I want to do that? Well, if we factor out a 2 from the numerator, we get 2 times y plus 1 squared plus x minus 1 squared, which is exactly what we have in the square root in the denominator, x minus 1 squared plus y plus 1 squared. That's like we have root n under n. And if we have that, that all just simplifies to n. Now, root n. Now, of course, I'm thinking of n as this whole big expression here. So that on the right-hand side simplifies to 2 times the root of x minus 1 squared plus y plus 1 squared. So we have this inequality. 0 is less than or equal to our error function over the distance is less than or equal to this root function. Now, if we apply the Squares Theorem, the limit as xy goes to 1 minus 1 of 0, well, that is clearly equal to 0. And it is equal to the limit as xy goes to 1 minus 1 of this root as well. This root, if I plug in the 1 and the minus 1 here, I will get 0, and so the limit on the right-hand side is 0 as well. And therefore, by the Squeeze theorem, the limit as xy goes to 1 and minus 1 of our fraction, which is the error function over the distance, that is equal to 0 also, and therefore our function f of xy is differentiable at the point 1 minus 1. In the next video, we'll take a look at an example where a function is not differentiable at a certain point.